Unit 1 Global Carbon Balance. The global carbon balance, also known as the carbon cycle, refers to the movement of carbon, in various forms, through the Earth's atmosphere, oceans, ecosystems, and geosphere. It is a fundamental process that plays a crucial role in regulating the Earth's climate and sustaining life on our planet. Understanding the global carbon balance is essential for addressing climate change and managing carbon emissions. The global carbon balance is typically described as being in a state of equilibrium over long time scales, meaning that the rate of carbon uptake by sinks roughly equals the rate of carbon release from sources. However, human activities, especially the burning of fossil fuels and deforestation, have disrupted this balance by releasing large amounts of carbon into the atmosphere, leading to an increase in atmospheric CO2 concentrations. This excess CO2 is a primary driver of global warming and climate change. Efforts to address climate change involve reducing carbon emissions from human activities, enhancing carbon sinks through reforestation and conservation efforts, and finding ways to remove CO2 from the atmosphere through technologies like carbon capture and storage, CCS. Understanding and managing the global carbon balance are critical components of these mitigation strategies. Earth's carbon pools and fluxes. Earth's carbon pools. Earth's carbon pool refers to the various reservoirs or storage locations where carbon is found on our planet. These pools include both organic and inorganic forms of carbon and play a crucial role in the global carbon cycle, which influences Earth's climate and the availability of carbon for life on Earth. 1. Atmospheric carbon pool. Carbon dioxide, Colorado 2. The atmosphere contains a pool of carbon in the form of carbon dioxide, Colorado 2. Colorado 2 is released into the atmosphere through natural processes like respiration and volcanic eruptions and anthropogenic activities such as burning fossil fuels. Terrestrial carbon pools. Vegetation. Trees, plants, and other vegetation store carbon in their biomass through the process of photosynthesis. Soils. Soil contains a significant carbon pool, primarily in the form of organic matter. Organic matter decomposes, releasing CO2 into the atmosphere. 3. Aquatic carbon pools. Surface ocean. The surface layer of the ocean stores dissolved inorganic carbon, including bicarbonate, HCO3, and carbonate, CO3 squared, which are in equilibrium with atmospheric CO2. Deep ocean. The deep ocean contains a vast carbon reservoir, which exchanges carbon with the surface ocean over long time scales. 4. Geological carbon pools. Fossil fuels, deposits of coal, oil, and natural gas store large amounts of carbon deep underground. Human activities extract and burn these fuels, releasing CO2 into the atmosphere. Sedimentary rocks. Carbon can be stored in carbonate rocks, such as limestone, over geological timescales. Carbon fluxes. Earth's carbon fluxes are the various processes and pathways through which carbon moves between the different carbon pools or reservoirs on the planet. These fluxes are essential components of the global carbon cycle, influencing carbon levels in the atmosphere, oceans, land, and Earth's geology. Natural carbon fluxes. 1. Photosynthesis. Plants and phytoplankton absorb atmospheric CO2 during photosynthesis, incorporating carbon into their biomass. 2. Respiration. Plants, animals, and microbes release CO2 through respiration as they break down organic matter. 3. Decomposition. Dead plant and animal matter decomposes, returning carbon to the atmosphere and soil. 4. Volcanic activity. Volcanic eruptions release CO2 and other gases into the atmosphere. Anthropogenic carbon fluxes. 1. Fossil fuel combustion. The burning of fossil fuels for energy and transportation releases large amounts of CO2 into the atmosphere. 2. Deforestation. Clearing forests for agriculture and urban development reduces terrestrial carbon pools. 3. Land use changes. Agricultural practices, such as plowing and draining wetlands, can release carbon from soils into the atmosphere. 4. Industrial processes. Certain industrial activities, like cement production, release CO2 as a byproduct. Carbon footprints. A carbon footprint is a measure of the total greenhouse gas emissions, primarily carbon dioxide, Colorado-2, but also other gases like methane, CH4, and nitrous oxide, N2O, associated with a particular activity, product, organization, individual, or event. It represents the impact of human activities on climate change and is typically expressed in terms of carbon dioxide equivalent, Colorado-2e, which is a standardized unit that aggregates the global warming potential of various greenhouse gases. Carbon footprints can be categorized into two main types, direct and indirect. These terms refer to the sources of carbon dioxide, Colorado-2, emissions associated with an individual's or organization's activities. Understanding both direct and indirect carbon footprints is important for assessing and reducing one's overall environmental impact. 1. Direct carbon footprint. Direct emissions are those that occur from sources that are owned or controlled by an individual, household, or organization. Some common sources of direct emissions include fuel combustion. Emissions from burning fossil fuels for heating, cooling, and cooking in homes and buildings, as well as from operating vehicles and machinery. Industrial processes. Emissions from specific industrial activities that release CO2 and other greenhouse gases into the atmosphere. Agriculture. Emissions from livestock, manure management, and on-farm machinery. Example. If you drive a car powered by gasoline or use a natural gas furnace to heat your home, the CO2 emissions resulting from these activities are part of your direct carbon footprint. 2. Indirect carbon footprint. Indirect emissions are associated with the consumption of electricity, heat, or steam generated by someone else. Indirect emissions are typically generated off-site but are linked to the energy consumption of an individual, household, or organization. Examples. If you purchase electricity from a utility company that generates power from coal or natural gas, the CO2 emissions associated with the generation of that electricity are part of your indirect carbon footprint. Similarly, if you buy products that were manufactured and transported using fossil fuels, the emissions from those processes contribute to your indirect carbon footprint. Anthropogenic impacts on carbon footprints. It refers to the ways in which human activities contribute to and influence the amount of carbon dioxide, Colorado-2, and other greenhouse gases emitted into the atmosphere. These activities have a significant impact on global climate change, as they are a major driver of the increasing concentration of greenhouse gases in the atmosphere. Here are some key anthropogenic impacts on carbon footprints. 1. Fossil fuel combustion. The burning of fossil fuels such as coal, oil, and natural gas for energy production, transportation, and industrial processes is a major source of carbon emissions. This includes emissions from cars, trucks, power plants, and industrial facilities. Efforts to reduce fossil fuel consumption through energy efficiency and transitioning to renewable energy sources can lower carbon footprints. 2. Deforestation. The clearing of forests for agriculture, urbanization, and other purposes releases stored carbon into the atmosphere in the form of CO2. Additionally, The loss of forests reduces the planet's capacity to absorb CO2 through photosynthesis. Forest conservation and reforestation efforts can help mitigate this impact. 3. Land use changes. Converting land for various uses, such as agriculture or urban development, can release carbon stored in soil and vegetation. Land management practices, such as no-till farming and sustainable land use planning, can help minimize carbon emissions from land use changes. 4. Industrial processes. Certain industrial activities release greenhouse gases as byproducts. For example, cement production emits CO2 during the chemical conversion of limestone into clinker. Carbon capture and storage (CCS) technologies can be used to capture and store these emissions. 5. Waste management. Landfills and waste incineration produce methane, CH4, a potent greenhouse gas. Improved waste management practices, such as methane capture at landfills and increased recycling, can reduce these emissions. 6. Agriculture. Agriculture is a significant source of greenhouse gas emissions due to activities such as enteric fermentation in livestock, rice cultivation, and the use of synthetic fertilizer. Sustainable agricultural practices and innovations, such as improved livestock management and precision farming, can lower emissions from this sector. 7. Transportation. The transportation sector is a major contributor to carbon footprints through the use of gasoline and diesel fuels in vehicles. The adoption of electric vehicles, EVs, improved fuel efficiency, and the development of public transportation systems can reduce emissions from transportation. Physical and chemical methods of measurement of carbon dioxide. Carbon dioxide, Colorado 2, is a commonly measured gas in various industrial, environmental, and scientific applications. There are both physical and chemical methods for measuring the concentration of CO2 in a gas sample. Here are some of the most common methods. Physical methods. 1. Non-dispersive infrared, NDIR, spectroscopy. NDIR is one of the most widely used methods for measuring CO2 concentrations. It relies on the fact that CO2 molecules absorb specific infrared wavelengths. A gas sample is exposed to infrared light, and the amount of absorbed light is used to calculate the CO2 concentration. 2. Gas chromatography. Gas chromatography is a laboratory technique that separates and quantifies different gases in a sample. It involves injecting the gas sample into a chromatograph, where the CO2 is separated from other gases and detected using a thermal conductivity or flame ionization detector. 3. TDLAS, Tunable Diode Laser Absorption Spectroscopy. TDLAS is a highly precise method for measuring CO2 concentrations. It uses a tunable diode laser to scan across specific absorption lines of CO2. The amount of light absorbed is proportional to the concentration of CO2. 4. Gas detectors and sensors. Various gas detectors and sensors are available for continuous monitoring of CO2 levels in indoor environments, industrial settings, and research applications. These sensors often use technologies like electrochemical cells, infrared sensors, and chemical reaction-based sensors. 5. Gravimetric method. This method involves passing a known volume of gas through a solid adsorbent, usually a desiccant or soda lime, that will selectively absorb CO2. The increase in the mass of the adsorbent is used to calculate the CO2 concentration. Chemical methods. 1. Titration. In this method, a known volume of a gas sample is absorbed in a liquid solution, usually an alkaline solution, that reacts with CO2 to form a measurable product, typically a carbonate. The concentration of CO2 is determined by titrating the resulting solution with an acid of known concentration. 2. Chemical absorption. Colorado 2 can be absorbed from a gas stream by passing it through a solution or solvent that reacts with CO2 to form a compound. Commonly used solvents include sodium hydroxide, NaOH, or monoethanolamine, MA. The change in the properties of the solvent, such as pH or conductivity, is used to calculate the CO2 concentration. 3. Chemiluminescence. This method involves a chemical reaction between CO2 and a reagent that produces chemiluminescent light. The intensity of the emitted light is proportional to the concentration of CO2 and can be measured using a photodetector. 4. Infrared gas analysis. This is a chemical method that involves passing a gas sample through a tube containing a reagent that reacts with CO2 to produce a detectable infrared absorbing compound. The change in infrared absorption is used to determine the CO2 concentration.